The telescope was not supposed to find this. When engineers at NASA began designing the James Webb Space Telescope, the mission had a clear scientific purpose. Look back far enough in time, and you reach the epoch when the first stars ignited. The universe, in those earliest chapters, was supposed to be a rough and formless place. Hydrogen and helium, slowly gathering under gravity, small clumps of matter pulling together across hundreds of millions of years. A gradual process, patient, incremental. The kind of cosmic construction project that takes longer than any civilization has existed to begin producing recognizable results. That was the expectation. Not a guess, a prediction grounded in decades of observation, mathematical modeling, and a theoretical framework that had successfully explained nearly everything astronomers had pointed their instruments at. Then JWST opened its eye. The first deep field images arrived in the summer of 2022. Researchers who had spent careers building toward this moment sat with the data and began identifying the objects inside it. Galaxies, as expected. But the redshifts, the measurements that translate an object's light into a distance, and therefore a time, were coming back wrong. Not wrong in the sense of instrument error. Wrong in the sense that the objects were where they should not be, doing what they should not be doing, at a point in cosmic history when they should not yet exist. The galaxies were too big, not marginally, not in a way that could be absorbed by adjusting a parameter somewhere in the model. Some of the structures JWT identified in the early universe contained as much stellar mass as the Milky Way, a galaxy that took roughly 13 billion years to assemble, and they appeared to have reached that scale within the first few 100 million years after the Big Bang. By the timeline that cosmologists had trusted for decades, those galaxies had no right to be there. The first response from the scientific community was measured. Instruments this powerful introduced new calibration challenges. Redshift estimates at extreme distances carry uncertainties. There were reasonable grounds for caution. Researchers began working through the systematic checks, the kind of verification process that's science before a result graduates from anomaly to problem. The checks held. Over the following 2 years, as more data arrived and more teams analyzed it independently, the picture did not soften. If anything, it sharpened. Spectroscopic confirmation, a more precise method of measuring distance than photometric redshift estimates, returned consistent results. The galaxies were real. They were where the instruments said they were. And they were, by the standard model of cosmology, implausible. To understand why that word carries weight, it helps to understand what the standard model actually predicts. The framework is called lambda CDM. Lambda refers to the cosmological constant, the term Einstein introduced, and later called his greatest blunder, which now represents what we call dark energy. CDM stands for cold dark matter. Together, the two components account for roughly 95% of the energy content of the universe. The 5% left over is everything visible, every star, planet, gas cloud, galaxy, and person that has ever existed. Lambda CDM is not a rough sketch. It is one of the most precisely tested frameworks in the history of science. It correctly predicts the pattern of fluctuations in the cosmic microwave background, the faint thermal glow left over from the early universe, measured with extraordinary precision by satellites like Planck. It correctly predicts the large-scale distribution of galaxies across cosmic time. It correctly predicts the abundances of light elements produced in the first few minutes after the Big Bang. Astronomers have spent decades trying to break it, and it has held. Within that framework, galaxy formation follows a process called hierarchical assembly. Small structures form first. Dark matter halos collapse, pulling ordinary matter with them. Stars ignite inside those halos. Over hundreds of millions of years, halos merge and grow. Galaxies form, collide, absorb one another, and gradually become the large and complex systems we observe in the nearby universe today. The process is slow because it has to be. Gravity operates at the speed of physics, and the early universe was expanding rapidly, making it harder for matter to concentrate. What Lambda CDM does not predict is a universe that skips the early stages. It does not predict galaxies, with the stellar mass of mature systems appearing less than 1 billion years after the Big Bang. It does not predict structures that look, in some cases, as evolved and settled as galaxies we see in the much more recent universe. And yet the objects JWST found are not at the edge of what the model can explain. Some of them appear to sit well outside it. One early estimate, published in a paper that drew significant attention in 2023, suggested that several of the candidate massive galaxies exceeded the theoretical upper limit on what could have formed by that point in cosmic history, not by a small margin, but by enough that the authors described the tension as potentially serious. The language in the paper was careful, as it should be, but the direction was clear. Something in the timeline is not behaving the way the model said it would. The question that followed was the right one to ask, even if the answer has not arrived yet. Was this a problem with the observations? A problem with a specific piece of the model? Or something deeper, a sign that the framework itself, for all its successes, had been missing something that only a telescope powerful enough to see the first 1 billion years of cosmic history could reveal? That question is still open. And the fact that it is still open after 2 years of serious investigation by some of the most careful observers in modern astronomy is itself the first piece of evidence worth sitting with. Before the implications can land properly, the mechanics need to be clear. Galaxy formation, under the standard framework, OX, is not driven by the visible matter we can see. It is driven by dark matter, a substance that does not emit, absorb, or reflect light, and whose existence we infer entirely from its gravitation effects on the things we can observe. The rotation curves of galaxies, the bending of light around galaxy clusters, the large-scale structure of the cosmic web, all of it points toward the same conclusion. Most of the matter in the universe is something we cannot directly detect, and it is doing most of the gravitational work. Dark matter halos form first. They are the scaffolding. Ordinary matter, hydrogen, helium, the raw material of stars, falls into those halos, cools, and eventually collapses into stellar nurseries. Stars form. The first generation are thought to have been massive, short-lived, and violent in their deaths. They seeded the surrounding gas with heavier elements. A second generation followed, incorporating those metals. Over time, stellar populations built up inside growing halos, and those halos merged under gravity into larger structures. The process repeated across billions of years, until the universe began to look the way it does now, organized into filaments, nodes, and vast emptiness, with galaxies concentrated where the dark matter is densest. The timeline this process requires is not arbitrary. It is set by physics. The rate at which dark matter halos grow is constrained by the expansion rate of the universe. In the very early universe, that expansion was rapid, and the density fluctuations, seeding structure formation, were small. The model predicts with reasonable precision how much mass should have assembled into halos of a given size by any given cosmic epoch. And it predicts that the largest, most massive halos, the ones capable of hosting giant galaxies, should not exist in significant numbers during the first 1 billion years. JWST did not receive that memo. The objects that caused the most serious concern were a class of early galaxies that researchers began calling informally the little red dots. The name came from their appearance in the infrared imaging compact, faint in some bands, but with properties suggesting either enormous stellar mass, extremely high star formation rates, or both. Some of them appeared to be forming stars at rates hundreds of times higher than a galaxy like the Milky Way does today. A few appeared to contain supermassive black holes at their centers, objects that, by our current understanding of black hole growth, should not yet have had enough time to reach those masses. Each of those observations is individually interesting. Together, they form a pattern. The pattern is not that the early universe was active. Some level of early activity was expected. The universe was denser then. Gas was more abundant. And the conditions for star formation were in some ways more favorable than they are today. What the model did not predict was the scale. Not just that stars were forming, but that they were forming fast enough and in sufficient concentrations to produce galaxies comparable in mass to the largest systems in the present-day universe, and doing so within a window of time that the standard framework describes as the opening act, not the main event. One way to think about the problem is in terms of efficiency. Under lambda CDM, the conversion of available gas into stars follows a well-constrained efficiency curve. Only a fraction of the gas in a halo actually collapses into stars at any given time. Feedback processes from supernovae, radiation pressure, and the jets from active galactic nuclei all work to push gas out of galaxies and slow star formation. The model incorporates this. It has to, because without those feedback mechanisms, simulations produce too many stars too quickly, even in the nearby universe. But the early massive galaxies, JWST, found appear to have formed stars at efficiencies that strain or exceed what the model allows. Some estimates suggest that to produce the observed stellar masses in the available time, those galaxies would have needed to convert gas into stars at rates approaching the theoretical maximum or beyond it. That is not a rounding error. That is the model being asked to do something it was not built to do. Several explanations have been proposed, and none of them is fully satisfying yet. One possibility is that the initial mass function, the distribution of stellar masses when a new population of stars forms, was different in the early universe. If early stellar populations were weighted more heavily toward massive stars, those stars would burn brighter, live shorter lives, and release more energy per unit of gas consumed. The galaxy would appear more luminous for its mass than a galaxy forming stars under present-day conditions. This would make early galaxies look more massive than they actually are, a bias in our measurements rather than a violation of the model. That explanation has some theoretical support. There are reasons to think that the conditions in the early universe, lower metallicity, higher gas temperatures, different radiation environments, might have favored the formation of more massive stars. But quantifying the effect is difficult, and the observational evidence for a dramatically different early mass function is not yet conclusive. A second possibility involves the role of dark matter itself. Some researchers have explored whether modifications to the standard cold dark matter, picture models involving warm dark matter, or dark matter with self-interactions, could allow structure to form more efficiently in the early universe. The idea is that if dark matter behaves slightly differently than lambda CDM assumes, the halos that host galaxies might be able to assemble faster, giving galaxies more time to grow. These alternatives are not new. They predate JWST. What JWST has done is sharpen the question, given the community a set of observations precise enough to test which explanations survive contact with the actual early universe, and which ones do not. So far, none of the proposed solutions has cleanly resolved the tension without creating new problems elsewhere. That is where the investigation currently stands, not at a conclusion, at a junction where the evidence is clear enough to take seriously, and the explanations are numerous enough to suggest that something genuinely uncertain remains at the center of the problem. The deeper question is not which parameter needs adjusting. It is whether the framework that the parameter lives inside is still the right one to be using. There is a version of this story where the anomalies dissolve. Science has a long history of apparent crises that turned out to be calibration problems. Instruments misread. Pipelines introduce systematic biases. Early results at the edge of detection sensitivity get revised when larger samples arrive. The history of observational astronomy in particular is full of moments where a striking finding a galaxy at an impossible distance, a star with an impossible age, a measurement that contradicted. The model softened under scrutiny and eventually found a comfortable home within the existing framework. That history is not irrelevant here. It is part of why the researchers working with JWST data have been careful. That the claims being made are large enough that the burden of proof is correspondingly high, and the scientific community has been applying that standard seriously. But 2 years into the analysis, the data has not softened in the expected direction. Some of the most dramatic early estimates have been revised downward. The initial photometric redshifts, measurements derived from the color of light across multiple wavelength bands, rather than from the detailed spectral analysis that gives more precise results, carried uncertainties that allowed for a range of interpretations. A few of the candidate objects at extreme distances turned out, on closer inspection, to be at somewhat lower redshifts than first reported. The stellar mass estimates for some objects were adjusted as more sophisticated modeling of their stellar populations was applied. This is the normal process of science. Early results get refined. The problem is that the refinements have not been enough to make the tension disappear. The galaxies that remain after the most careful vetting are still, by a meaningful margin, in tension with what Lambda CDM predicts. Not every object in the original sample, but enough of them confirmed spectroscopically with mass estimates that have survived multiple rounds of scrutiny to prevent the issue from being dismissed as noise. The Cosmic Evolution Early Release Science Survey, one of the major early JWST programs dedicated to studying galaxy formation, returned results that the research team described as surprising even after accounting for known sources of uncertainty. The JWST Advanced Deep Extragalactic Survey produced similar findings. In teams working with different data reduction pipelines and different modeling assumptions have arrived at overlapping conclusions. At some point, consistency across independent analyses becomes its own form of evidence. What makes the situation scientifically interesting, rather than simply puzzling, is that the tension is not uniform. It is concentrated in specific types of objects, at specific redshifts, with specific properties. The most problematic galaxies tend to be compact, smaller physical size than their mass would suggest if they had formed the way galaxies form in the nearby universe. They tend to have high star formation rates, or in some cases to have already shut down star formation entirely, a state called quenching, at a point when the universe was less than 2 billion years old. That second detail is particularly uncomfortable. Quenched galaxies in the early universe represent a double problem. Not only must the model explain how those galaxies assembled their stellar mass so quickly, it must also explain how they stopped forming stars so quickly. Quenching is not simple. In the nearby universe, the process is tied to feedback from supermassive black holes at galactic centers, which heat and eject gas, cutting off the supply of raw material for new stars. That mechanism takes time to operate. It requires the black hole to grow large enough, accrete enough material, and generate enough energy to affect the surrounding galaxy. Finding quenched galaxies in the early universe therefore implies not just rapid assembly, but rapid assembly followed by rapid shutdown. Two processes, both of which the model predicts should be slow, appearing to have run their full course within a fraction of the time the framework allots them. One researcher described the situation in a paper published in late 2023 as galaxies that appeared to have lived an entire life before the universe had given them time to begin one. The phrasing is careful enough to be scientific and striking enough to be honest about what the data is showing. The proposed solutions have continued to multiply. Beyond the stellar mass function arguments and the dark matter modifications discussed earlier, some researchers have pointed to the possible role of primordial black holes that may have formed in the very early universe, before stars existed, and which could have seeded the growth of supermassive black holes more quickly than the standard stellar collapse pathway allows. Others have explored whether the cosmological constant itself, the term that drives the accelerating expansion of the universe, might behave differently at early times than it does today, subtly altering the conditions under which structure forms. Each of these ideas is speculative in ways that the standard framework is not. Lambda CDM earned its position through decades of successful predictions. The alternatives are newer, less tested, and in most cases have not yet made predictions precise enough to be definitively confirmed or ruled out by the current data. That asymmetry matters. A framework that explains everything is not automatically right, but a framework that explains almost everything is not easily displaced by a collection of anomalies, however striking, that lack a clearly superior replacement. This is where the sociology of science and the logic of evidence come into mild tension. The conservative position that lambda CDM is essentially correct, and the anomalies will eventually be explained within it, is not unreasonable. It is, in fact, the scientifically responsible default. Extraordinary claims require extraordinary evidence. The history of physics is littered with anomalies that turned out to be manageable, and revolutions that turned out to be premature. But the conservative position is not the same as certainty. What the JWST data has done, whatever its final interpretation turns out to be, is put a number on something that previously existed only as a theoretical comfort. The early universe before these observations was largely inferred. The models were constrained by the cosmic microwave background, by the large-scale structure of the nearby universe, by simulations run forward from initial conditions. JWST is the first instrument capable of directly observing galaxy formation at the epochs the models describe in detail. And what it found in those epochs was not exactly what the models drew. The gap between the prediction and the observation may close. The explanation may arrive in the form of a revised stellar mass function, a modified feedback prescription, a better treatment of dust obscuration, or some combination of factors that shifts the numbers enough to restore consistency. That outcome is possible, and by the prior track record of the framework, perhaps even likely. But the gap has not closed yet, and while it remains open, the question it carries remains active. Whether the most successful cosmological framework in the history of science is complete, or whether the first clear view of the universe's earliest chapters has found the edge of what that framework was built to explain. There is a harder version of the question that most papers do not lead with. The technical literature on JWST anomalies is careful, precise, and appropriately hedged. It discusses stellar mass functions and feedback prescriptions and photometric calibration. It proposes modifications to specific parameters and tests them against available data. It is, in the best sense, science working the way science is supposed to work methodically, with attention to uncertainty, resistant to conclusions that outrun the evidence. But underneath the technical language, there is a question that the data keeps pushing toward, even when the papers themselves do not say it directly. What if the timeline is wrong? Not wrong in a minor sense. Not wrong in the sense that a parameter needs adjustment, or that a feedback mechanism was slightly underestimated, or that early stellar populations were somewhat different than assumed. Wrong in the sense that the sequence of events we have constructed for the first billion years of cosmic history, the sequence that lambda CDM predicts with apparent precision, may not accurately describe what actually happened. That possibility is uncomfortable in a way that goes beyond the usual discomfort of scientific revision. It is not like discovering that a planet has an extra moon, or that a particular star is slightly older than previously measured. The timeline of cosmic structure formation is not a peripheral detail. It is load-bearing. It connects to the age of the universe, the nature of dark matter, the behavior of dark energy, and the physical processes that eventually produced every galaxy, star, and planet that exists. Getting it wrong in a fundamental way would not simply require adding a correction to one corner of the model. It would require understanding why a framework that correctly predicts so many other things failed at this particular junction. That question has a precedent, and the precedent is instructive. In the late 1990s, two independent teams of astronomers were measuring the rate at which the universe's expansion was decelerating. The expectation, grounded in a universe filled with matter and radiation, was that gravity would be slowing the expansion down. The measurements came back showing the opposite. The expansion was accelerating. Something was pushing outward with enough force to overcome the gravitational pull of all the matter in the observable universe. That result was not immediately celebrated. It was checked, rechecked, and approached with significant skepticism. The systematic errors possible in measuring distances to Type A supernovae at cosmological distances were well known. The result was extraordinary, and the scrutiny was proportional. The result held. The cosmological constant dark energy was reintroduced into the equations, and lambda CDM was born in its modern form. The framework that now predicts galaxy formation timelines was itself the product of an observational surprise that forced a revision of the previous model. The reason that history matters is not to suggest that JWST has already produced an equivalent revolution. It has not. The evidence is not yet at that threshold. But the precedent establishes something important. The standard model of cosmology has been revised before, in response to observations that could not be explained within the previous framework, and the revision produced a better model rather than a collapse of understanding. If the JWST anomalies eventually require a similar revision, not a parameter adjustment, but a structural change to some piece of the framework, that would not be a failure of science. It would be science functioning at its highest level. The question is what that revision would need to look like, and whether any of the currently proposed alternatives are capable of filling the role. This is where the investigation becomes genuinely difficult. The most discussed alternative to standard cold dark matter involves a class of models. Dark matter particles have slightly different properties. Either a higher velocity at early times, which would suppress the formation of small structures, or self-interactions that alter how halos form and merge. These warm or self-interacting dark matter models have been explored for years, primarily in response to discrepancies between lambda CDM predictions and observations of small-scale structure in the nearby universe. The number of satellite galaxies around the Milky Way, the density profiles of dwarf galaxies, and related puzzles. The interesting thing about the JWST results is that they push in the opposite direction. The small-scale structure problems with lambda CDM suggest that the model produces too much small-scale structure. The JWST massive galaxy problem suggests that at early times, the model produces too little large-scale structure. Those two tensions are not obviously compatible with the same modification to the dark matter model. A change that helps with one might worsen the other. That asymmetry has not gone unnoticed. Some researchers have proposed that the resolution lies not in the dark matter at all, but in the baryonic physics, the behavior of ordinary matter, gas, stars, and radiation that sits on top of the dark matter scaffolding. The argument is that current simulations may be missing feedback processes that were particularly efficient in the early universe, or overestimating the degree to which early star formation was suppressed. If the baryonic physics can be tuned in ways that are physically motivated, rather than ad hoc, the tension with JWST might dissolve without touching the dark matter model at all. This explanation is attractive, precisely because it is conservative. it leaves the largest and most successful pieces of the framework intact and asks only that the smaller scale physics be revised. Whether it is sufficient is an open question. The simulations required to test it are computationally demanding, and the parameter space is large enough that ruling out baryonic solutions definitively will take time. There is a third possibility that receives less attention in the technical literature, but that deserves to be stated plainly. Lambda CDM contains two components whose physical nature remains essentially unknown. Dark matter has been inferred from its gravitational effects for decades, but no direct detection experiment has confirmed its particle identity. Dark energy has been measured through its effect on the expansion rate, but its fundamental nature, whether it is a true cosmological constant, a dynamic field, or something else, entirely remains an open question. The framework works, but it works by incorporating two major unknowns as fixed terms in the equations, and then testing the predictions those terms produce. If either of those terms behaves differently at early cosmic times, then the model assumes if dark energy was stronger or weaker in the first billion years, or if dark matter had properties in that epoch that differ from its behavior today. The predictions for early galaxy formation would change. The model would still be approximately right about everything it has been tested against in the nearby universe, while being systematically wrong about the early universe in ways that only an instrument like JWST could reveal. That is not a prediction. It is a possibility. But it is a possibility the data has made harder to ignore. Step back from the models for a moment and consider what is actually being observed. Light travels at a fixed speed. When astronomers point JWST at an object 13 billion light-years away, they are not seeing that object as it exists today. They are seeing it as it existed 13 billion years ago. Light that left its source when the universe was a fraction of its current age, spent billions of years crossing the expanding space between, and arrived at the telescope's mirror, carrying information about a time that no longer exists anywhere in the observable universe. This is not a metaphor. It is the literal mechanism by which cosmology works. Every deep field image is a time machine with no moving parts. The further the object, the further back in time the observation reaches. What JWST has done is extend that reach further than any previous instrument, with enough sensitivity and resolution to do more than simply detect distant objects. It can characterize them, measure their stellar masses, estimate their star formation rates, identify the spectral signatures of specific elements in their light, determine whether they host active supermassive black holes. The telescope has turned the early universe from a place that could be inferred into a place that can be examined. And examination, as it turns out, is different from inference. For decades, cosmologists built models of early galaxy formation and tested them against two types of evidence: the statistical properties of the cosmic microwave background, which encodes information about the universe roughly 400,000 years after the Big Bang, and the distribution of galaxies in the relatively nearby universe, which reflects conditions billions of years after the epoch JWST is now probing. The gap between those two data sets, the first billion years of cosmic history, was largely reconstructed through simulation rather than direct observation. Simulations are only as good as the physics they encode. If the physics is right, the simulation produces a universe that resembles the one we observe. Lambda CDM simulations, at the large scales where they have been most thoroughly tested, do produce universes that resemble ours. The large-scale structure, the cosmic web of filaments and voids, the statistical properties of galaxy populations across a wide range of epochs, all of it matches the observations with impressive precision. But simulations are run forward from initial conditions. They do not observe, they predict. JWST observes. The distinction matters because predictions and observations do not always agree in the details. A simulation that correctly reproduces the statistical properties of a galaxy population does not necessarily correctly reproduce the individual histories of the most extreme objects within that population. The most massive, most rapidly assembled, most quickly quenched galaxies in the early universe are by definition rare outliers, the tail of a distribution. And the tails of distributions are where models are most often wrong, because the physics of extreme cases is harder to capture than the physics of typical cases. What JWST is showing is the tail of the early galaxy distribution extends further than the simulations placed it. Whether that is a problem with the simulation's input physics, their resolution, their treatment of feedback, or something more fundamental about the underlying model is still being determined. But the observation itself is not in serious dispute. The galaxies are there. They are massive. They are early. And the simulations did not predict them at the frequency or at the scale at which they appear. There is a related observation that has received somewhat less public attention, but that carries its own weight in the technical discussions: the supermassive black holes. Several of the early massive galaxies, JWST has confirmed harbor black holes at their centers whose masses are, by the standard formation pathway, extremely difficult to explain. Black holes grow by accreting matter pulling in gas, dust, and occasionally other compact objects, and the rate at which they can grow is physically limited by a mechanism called the Eddington limit. Above that rate, the radiation pressure from infalling material becomes strong enough to push material outward, effectively capping how fast the black hole at any given moment. Growing a black hole of 1 billion solar masses or more from a stellar remnant of a few tens of the kind left behind when a massive star collapses takes time under this constraint. The standard estimate, depending on the assumed accretion efficiency and duty cycle, runs to hundreds of millions of years at minimum, and more comfortably to over 1 billion years. Finding black holes of that scale in galaxies that existed less than 1 billion years to the Big Bang compresses that timeline uncomfortably. The same categories of explanation apply here as for the galaxy mass problem. Perhaps the initial seeds were heavier primordial black holes formed in the early universe, before stars existed, bypassing the stellar collapse pathway entirely and starting the growth process from a much higher initial mass. Perhaps accretion proceeded at super Eddington rates for extended periods, something that is theoretically possible under specific conditions, but poorly constrained observationally. Perhaps the black holes grew through mergers more efficiently than the models capture. Each of these is a real proposal, supported by some theoretical reasoning, and, in some cases, preliminary observational hints. None of them is yet established as the dominant pathway. What they share is the common structure of explanations proposed after the fact to account for observations that the prior model did not anticipate. That is not a mark against them. Science regularly proceeds this way, and post hoc explanations that survive subsequent testing become the new standard. But it does mean that the field is currently in a state where the observations are ahead of the theory, where the universe, observed directly for the first time in its earliest chapters, is doing something that the most careful prior predictions did not fully capture. That state is temporary. Models will be revised. Simulations will be improved. Spectroscopic surveys will confirm or revise the mass estimates. The tension will either dissolve into a refined version of the existing framework, or it will sharpen into something that requires a more structural response. But temporary does not mean unimportant. The period when observations outrun theory is precisely the period when the most interesting science happens. When the framework is being tested against reality in the domain it was least prepared for, and when the results of that test are still coming in. The JWST data is still coming in. Every new observing cycle returns more objects at higher redshifts with better spectroscopic coverage. probing the early universe in more detail than the cycle before. The sample that caused concern in 2022 and 2023 is not the final sample. It is the opening round of a much longer investigation, one that will continue to accumulate evidence long after debates about parameter adjustments and model modifications have been settled or superseded. The telescope is still looking, and the universe observed directly at its earliest accessible moments has not yet finished showing what it was doing before anyone was there to see it. Return to the original expectation, a universe that begins simple, matter distributed nearly uniformly, with only the faintest density variations, 1 part in 100,000 seeding everything that follows, gravity working on those variations across hundreds of millions of years, small structures forming first, then larger ones still, a patient, hierarchical process building complexity from simplicity across timescales that dwarf anything a human civilization can hold in mind. That picture was not arbitrary. It emerged from observations, from mathematics, from a framework tested against the most precise measurements in the history of cosmology. It described a universe that made sense, not comfortable sense, not human sense, but physical sense, a universe operating under laws that produced predictable timelines. JWST looked at the earliest accessible window of that timeline and found galaxies that had not read the schedule. What that finding means, finally, stripped of calibration caveats and parameter discussions, is that the universe formed structure more efficiently than the model predicted, in the epoch the model was least prepared to have checked. At a time when no instrument before JWST could have seen it clearly enough to be certain. That combination is not coincidence. It is the shape of a boundary. Every scientific framework has a domain of validity, the range of conditions and haskell's within which its predictions are reliable. Lambda CDM was built from and tested against observations of the nearby universe, and the very early universe at the moment the cosmic microwave background was released. The billion-year gap between those two datasets was filled by simulation and inference. It was the one stretch of cosmic history where the model had made detailed predictions, without having those predictions subjected to direct observational test. That gap has now been opened. The question the JWST data raises is not whether Lambda CDM is wrong in general. The evidence does not support that conclusion, and the framework's successes are too numerous and too precise to be dismissed. The question is more specific, and in some ways more interesting. Whether the model's predictions for the earliest epoch of galaxy formation, the predictions that were built without the benefit of direct observation, are accurate in the ways the model assumes, or whether they are capturing something real but incomplete. Incomplete is a particular kind of wrong. It is not the wrong of a framework that has been refuted. It is the wrong of a framework that is missing a piece, a physical process, a property of dark matter, a behavior of early stellar populations, a mechanism of black hole seeding that matters in the extreme conditions of the early universe, even if it is negligible in the conditions where the model has been most thoroughly tested. Finding that piece, if it exists, will require more than JWST data alone. It will require theoretical work capable of translating the observations into constraints on the underlying physics. It will require simulations sophisticated enough to test proposed modifications against the full range of available evidence, not just the early galaxy population in isolation. It will require the patience that serious science requires and the willingness to follow the evidence into conclusions that were not anticipated when the questions were first framed. That process is underway. But there is something worth holding on to before it resolves a detail that sits at the edge of the technical discussion and does not quite fit inside it. The galaxies JWST found in the early universe are not simply data points. They are places, structures that contain stars, billions of them, inside a halos of dark matter, In a universe that was less than 1 billion years old, those stars lived and died. The most massive among them lasted only a few million years before collapsing, seeding the surrounding gas with the elements their fusion had produced. Successive generations of stars formed in that enriched material. The process repeated, layer by layer, building the chemical complexity that eventually, billions of years later, in other galaxies, under different conditions, would make something like a planet with an atmosphere, an ocean, a surface warm enough for chemistry to persist. The timeline that JWST is complicating is also the timeline that leads here. If the early universe was more efficient at building structure than the model predicted, then the conditions for complexity arrived earlier than the model suggested. Galaxies matured faster. Heavy elements were produced sooner. The long chain of physical and chemical processes that eventually connects a collapsing gas cloud to something capable of looking back at the sky was, perhaps, initiated at an earlier point in cosmic history than the standard picture placed it. That implication does not resolve into a clear conclusion. The connection between early galaxy formation and the eventual emergence of life-bearing planets is long contingent and poorly constrained. Nothing in the JWST data speaks directly to that connection. But the direction is worth noting. A universe that builds complexity faster than expected is a universe where the window for that complexity is wider than the model suggested, where the first possible moment for the emergence of chemistry and the structures chemistry eventually produces may have come earlier than the timeline that was assembled before JWST opened its eye. Whether anything was there to notice that window is a different question entirely. Whether anything will be there to notice it. The next time the timeline turns out to have been underestimated, whether the process that produces observers also outpaces the predictions built in their absence is a question the current evidence cannot answer. It may not be a question the current framework was built to ask. The telescope is still looking. The early universe is still returning its light, one observation at a time, across a distance so large that the signal takes longer to arrive than the entire span of recorded human history. And the galaxies at the far end of that signal, massive, early, improbable by the standards of the model that preceded their discovery, are still there, having done what they did long before the question of whether it was possible had been asked.